Welcome to Prerequisite Course number 135, and today we're talking about the effects of Gurney flaps on F1 cars, in particular the front wing section. And in podcast number 126, 127, and 128, we looked into the Gurney flaps on road cars. Now we're looking at the F1 version, and if you haven't checked those podcasts out, check them out because they are quite interesting. We look at quite a few different types of flow control devices and quite surprising. So Gurney flaps, they've been around for quite a long time in the aerospace industry, in the aeronautical industry, for probably 40-50 years, and their effects are incredibly beneficial. So like when you put a Gurney flap onto an airfoil, it's not uncommon for that airfoil to experience like a 10, 20, 30, 40% increase in lift, depending how big the Gurney flap is and the airfoil in general. And often this increase in lift does not come with that greater drag penalty. So they are incredibly beneficial. And for those of you who don't know what Gurney flaps look like, let me quickly draw what they are. And if you're listening to this on Spotify or Google Play or whatever, you can see this on Spotify, the video, and or YouTube. And on YouTube, we have other goodies as well that you probably like. So let's say we have an airfoil, and I'll describe it to you as well here. Let's say we have an airfoil, and the flow is coming on this way. And the airfoil is producing lift up here. So it's going up. We have the Gurney flap that comes down. And it's just this little flap that pops down, usually 90 degrees down, so it's like quite vertically down. Now, if you have the opposite situation where you have an airfoil producing downforce, so it's pitched the other way, and we have the flow coming in, we'll then put the Gurney flap up. So it's producing downforce, so the force is going down here. And that is typically what's happening on cars. So we don't have the Gurney flap actually going down, it goes up. And that's just because it works well with lift production. That's how we use it. So that's what a Gurney flap is. And as I mentioned, it has incredibly beneficial results for airfoils in general. And that's why we're looking at it in this podcast. So they say the paper that we're looking at to look into this is called Aerodynamic Effect of the Gurney Flap on the Front Wing of an F1 Car and Flow Interactions with the Car Components. And this is open access, so you can find a link in the description. And if you want to play along at home. And they say here, in terms of racing cars, that in racing cars, the component has a height of about 1 to 5% as the ratio between its height and the chord of the wing. So this Gurney flap is about this big, 1 to 5% of the wing that is attached to that chord. So it's quite small, but it has such a massive effect. And they say the macroscopic effect of the flap is an increased flow deflection due to both flow recirculation on the pressure side and an increased lower base pressure at the trailing edge. So in other words, this flap that is pointing up here is redirecting the flow more up very violently, I would say. So that also results in the flow that's on the pressure side, so the underside of the wing, to also pop up as well. That dramatically increases the downforce. And they say here that increases the airfoil loading and therefore the downforce. But also, in addition to this, they have the local effects of the suction side separation bubble at low heights from the ground can increase related drag. So what they're saying here is that, let me pop back over to our paint section here. So what I was saying here is that with this situation here where we have the Gurney flap going up, the flow comes along and then it hits this and then gets redirected quite violently, and then this flow will also come along as well like this. But they also say with the let me draw another one here. Let me say we have like a fairly violent one here, and we have the flow coming along. We may get a flow separation bubble around here, and that can increase the drag, especially when we are very close to the ground. So that's one detriment of the Gurney flap on the airfoil's aerodynamics. But if it's well designed, Gurney flaps can improve the aerodynamics of cars, as we saw in podcasts 126, 127, and 128, where there was like a 10 or 20% increase in effectively the efficiency of the downforce that's being produced. Now, these researchers also say that if the Gurney flap is mounted on thicker ailerons, the drag can be reduced because vortices break off further downstream of the profile, keeping the boundary layer attached and stable for a wider incidence and ground height range with respect to the baseline case. Okay, so let me say in plain English what this means and what they're referring to here. So this is a fairly, a fairly quick explanation of what they're trying to say here. That they just explain it and then they move on. So let's say we have an airfoil and the flow is coming this way. So if we have a very thick airfoil, let me draw a bit of a cross section here. If we have a fairly thick airfoil, the flow comes from the bottom to the top in this case, because we have lift being produced upwards, or whichever direction you want. I'm just going to say that's going upwards, and we have the flow now is going to try to bleed from the bottom to the top. That's a typical airfoil, and this results in a wingtip vortex that goes downstream, and that, as we know, is typically associated with a lot of drag. That's called induced drag. The reason why it's called induced drag is because it is lift-induced drag. We are using the lift that we are producing is inducing this drag. That's the terminology. So what they're saying here is this Gurney flap, which in this case will be going down, like this situation here, is now preventing this vortex from breaking off further upstream. So it actually stays attached as we go downstream, and it might break off the airfoil further downstream. So it might start off here, but it migrates down to here. So we save this much distance. With this, we get a reduction in the drag. Also, potentially what we get is a change in the boundary layer profile, which then can also increase the airfoil's properties as well. So that's what that all meant, what they were trying to say here. They also say that a lift enhancement above 10% has been observed by other researchers by comparing the clean DU91W2250 airfoil, which is a wind turbine airfoil, compared to one with a Gurney flap. So I hope you're getting the understanding that these Gurney flaps are used in so many different situations, not just F1 cars or racing cars, but also wind turbines and airfoils, which is where they came from to begin with. So they are incredibly versatile, and they have such a good effect on airfoil aerodynamics. Now, about their current paper, what they're going to be looking into, they say that in this paper, the CFD analysis of the aerodynamic performance of the front wing of an F1 car is presented to understand the effects of a Gurney flap on a multi-element wing. The flow structures with and without the Gurney flap are investigated to also highlight the interactions with downstream car components. So in other words, they're looking at the effects of a Gurney flap on an F1 car, and they want to see how that affects the lift, drag, and the different components around the nose section, and then also the flow vis breakdown. I should mention in this podcast, we're going to be looking at the setup, so the theory of the Gurney flap, then the setup in their CFD, analyzing that, then the effects of the Gurney flap on the overall lift and drag component coefficients of the car, then looking at the different components of the car, so the like front wing, flap, end plates, tire, suspension, and the nose, the effects of the Gurney flap on the lift and drag coefficients of each one of these components. Then in the next podcast, we'll delve into the flow vis. So we'll look at how the Gurney flap is manipulating the flow and how that then resulted in the drag changes and the changes that we are seeing in this podcast. I think that's a good way of breaking this down. So let's talk about the F1 car geometry, because this is quite interesting and there's a lot of nuanced points here that we should cover. So they say that the 3D model of the real F1 car that they're using is from the 2000s, and it's used as the reference geometry for this analysis. And this car model is old compared to current models, but it is an actual car configuration that participated in the F1 championships for years. It can therefore be considered a relevant case in aerodynamic design for the scope of this paper. So the funny thing is that this paper was done in 2021. This is before some rule changes came in. So they had this geometry, which you can see in figure 1 here that I'm showing on our video. And if you look at the front wing setup, it's very simplistic. It's very simplistic. Like if you were to go to 2020, for example, there were most cars had 13, 14 elements, all just jutting out different ways to really mitigate the drag while increasing the downforce and manipulating where the flow is going to prevent it hitting the tire, for example, in a way that would increase the drag. But in 2022, I believe that's when they introduced in F1 the rules to simplify the front wing geometry. And the reason why they did this is because they found that the front wings that these teams were producing were so effective at pretty much deflecting the flow that it starved any trailing car from clean flow, and it really spoiled the downforce that this car could produce, which meant that this car had a far lower chance of overtaking a leading car. That meant that the competition was not nearly as competitive as what the organization wanted it to be. So they introduced this rule to simplify the front wing section. So these researchers didn't know at the time, but their research is actually more applicable now than what it was in 2021 because they're using a much more simplistic design here. So they actually got quite lucky, I guess, in a sense. So their design is actually quite, I would say, is quite applicable to today's cars, even more than it was when they first did this research. So that's quite funny. So let's talk about the CFD setup. So they say that the front wing setup includes a main wing, a flap with a Gurney flap, so you can see these little pink bits here, and some end plates, so on the sides here. The Gurney flap is installed perpendicular to the trailing edge of the flap, so it's going straight up, and the height of the Gurney flap is around about 1%. It changes, of the chord of the flap, I should mention, but it changes, so you can see here that's like 1.8%, then it goes to like almost nothing, then it goes back up to about 1.5, so on average it's about 1% of the flap's chord. So they used the SST K Omega terminus model for their CFD, which means immediately you know they're probably using either RANs or DES. In this case, it is RANs, because only these general types of CFD use these terminus models. So far, I guess I should say, maybe in the future they might come with different ones, I don't know. So let's talk about their CFD setup. With their domain, they specified the length of the vehicle from the front of the nose to the end of it. So they have really only the nose section, which includes the nose, the front wing section, the suspension to the tire, and the tire itself. And they designated the length of this geometry as LV. Now in figure 2, they show the CFD domain, and the domain size is arguably okay. So in other recent podcasts, I went through some CFD of other cars, and I mentioned how like their domain size was very inadequate, like it was way too small, which meant that the flow that's being developed is being really hampered, and it can't really develop properly, which means that the lift and drag forces are going to change dramatically. In this particular case, they have a very similar domain size, relatively speaking, to what we saw in the other podcasts. But this is a little bit of a twist. So the length of the domain, so from this distance from the inlet to the nose of the car, is 2 vehicle lengths. The distance of the end of the geometry to the outlet is only 4 vehicle lengths. So it's quite tight. And you might think that, okay, this is going to be a fairly small domain, it's inadequate. But the other thing is that compared to the other podcasts that we're talking about, this podcast is looking at a fairly streamlined body. So everything about this is streamlined except the tire, even the suspension is quite streamlined. So that means that we're not going to have too many upstream effects from this geometry, which indicates that the inlet location is not perfect, but it is not too bad. So, and the outlet is okay too, because we are going to be getting a fairly streamlined wake. So I would expect such a small domain to influence the aerodynamics by maybe a few %, but it's generally acceptable for this case. It's far better than if you were to put like a typical car body in here, which is much more bluff. A bluffer body needs to have a much bigger domain because it's not streamlined at all. You're really disturbing the flow. The flow has to go around and like balloon out. So you need to get the domain to take into account those changes. Now the width here is quite nice. There's a lot of room for the flow structure, for the flow to roll up into what it wants to roll up into unimpededly. So that's important because if you have the side walls very close, what that does is it accelerates the flow a lot, because you have the, let me go to paint here actually, and I'll draw it. It'll be a bit easier to draw, I think. So with pretty much anything, not just CFD, but with a wind tunnel as well. Let's say we are looking at the front on. So we have our wind tunnel or our CFD, whatever it is, and we have our object here on the wall. The bigger this object is, so let's say we have an object this big, we are now taking up a lot more of the cross-sectional area of this wind tunnel. So to begin with, we have all this cross-sectional area and the flow's coming in. Now the flow has to go around this object, which is really big. Now, if we reduce the cross-sectional area just by mass flow rate laws, it means that the flow has to go faster just to get through this section, because we have a smaller cross-sectional area now. We know that the mass flow rate equals rho VA. The density of air times the velocity that is going out times the area. If the area reduces and the density stays the same, the velocity has to increase. That's just how it works. So by doing that, we actually change the aerodynamics of the car and of the object in general, because we have to squeeze the flow and it goes faster, which changes its effectively the effective Reynolds number as well as all different other characteristics. Here they have a very big domain in terms of the side and the height of the roof, so that's quite nice. I'm quite happy with that. Now let's move on to their or they say in previous works, reference 26, the CFD model was validated by comparing the numerical results with detailed experimental data at different distances from the ground with different Gurney flap heights. So what they're saying here is that the CFD has been validated. They point us to other works, which in my opinion is never good because that should be included in this paper for a couple of reasons. One, I don't want to go to another work to find their validation data. It should be in the work that you're presenting. Two, this is often used as a way to increase the credibility of their CFD. I'm not saying that these researchers are doing it, but a lot of researchers do it where they use a different paper which they published their validation data in, and then they reference that paper to make it seem like the data, the validation process is good. But they might have published that in a bad paper or in a bad journal or with bad reviewers or something like that. They just got away with it. So then they can sort of like manipulate their general CFD worth by saying, okay, it's been published already, so it's good. Just because it's been published doesn't mean it's good. We've gone through quite a few papers in this podcast series of 135 podcasts that had really terrible CFD, and it was published. So that's not necessarily a vote of confidence. And I'm not saying these researchers are doing it, but it is a possibility. So in figure 3, they show the surface mesh of the geometry, and it's quite nice. It's quite well resolved. Interestingly, they have on their tires longitudinal grooves, and this is how old the F1 car is. So back in 1998, I think it was, they started looking at using using grooves on F1 tires and using them as well, and they don't use them anymore. So the question is, do longitudinal grooves affect the aerodynamics of a car in general, not just an F1 car, but cars in general? And the answer is yes. This is because these longitudinal grooves, and for those of you who aren't watching this, you can't see what I'm pointing out, but these longitudinal grooves are these circumferential grooves that go around a tire. They're like the big main grooves. For those of you watching this, you can just see where my mouse cursor is, and you can see these grooves here. So these grooves here funnel the air around the tire differently, and they also affect how the flow comes out around the contact patch. So we have the flow that will hit the tire, and it will go up and down, and around the sides as well. So the longitudinal grooves will give a little bit of resistance to the flow going left and right, so around the car, around the tire, the sides, which means that a bit more flow will be funneled up and down. What's more, as we get to the contact patch, if you have longitudinal grooves that are going underneath the tire, so through the contact patch area, it means that some flow can actually make it through to the other side of the tire without having to go around the sides. What this does is it reduces the size and the strength of what's called a jetting vortex. So what happens on a regular tire is that the flow comes around, goes down to the ground, then it has to be forced out around the side of the tire to get around the tire. And this results in this vortex being rolled up, and that's a jetting vortex. With these longitudinal grooves, that alleviates some of this jetting vortex situation here. So that's how longitudinal grooves affect a general car. In addition to that, they, in terms of F1 cars, they also increase the turbulence around the car and reduce the car's downforce. So there's that additional effect of these grooves on the car as well. Now, in terms of the general effects on the lift and drag, you might be looking at a few percent. I would say probably it's actually about 10 counts. So that's, in this particular case, about 2-3%. So it's not a huge effect on the car. So for the Y+, figure 4 shows that it is almost completely below 1, which is good. That's what you need for this SST K-Amiga approach. And the inlet velocity was set to 70 meters per second, which is 252 kilometers per hour, a fairly common F1 speed. So that's their CFD setup. Let's talk about the results of their research. So for the effects of the Gurney flap on the lift and drag coefficients, they say, as shown in figure 5 here, both the global downforce and drag in the front wing increases with the Gurney flap. That's not that surprising because we have seen that in a few other podcasts, and it is a fairly common situation to find yourself in. The lift, so the downforce here, and the drag increased by 24% and 28% respectively, while the aerodynamic efficiency decreased only by about 5%, so the lift to drag ratio. So we do get a significant increase in the lift coefficient, the downforce, but that's also accompanied by an increase in the drag. Is that a bad thing? Well, if you're on a track with a lot of corners, that's not necessarily a bad thing because you can then brake, like you can decelerate much quicker. So having an increase in lift is definitely great. We get a lot more downforce. With the increased drag, that's not necessarily too bad depending on the track. So that's something to keep in mind. Oh, but that's just for the car in general. We found that the overall geometry, the lift is increased by 24% and the drag increased by 28%. What about if we break it down to the different parts of the front wing? We have the main part, the flap, and then the end plates. So these effects, on the main wing, the Gurney flap is great. So it increases the downforce by 25% and reduces the drag by 68%. That's what we want for a lot of situations. So we are reducing the drag of the car while dramatically increasing the downforce. That's pretty sweet. But when it comes to the flap, so the second element on the wing, the second main element, a slightly different story unfolds. The Gurney flap still increases the downforce by about 50%, but it is accompanied by an increase in the drag coefficient, which is also about 50%. And again, this isn't necessarily a bad thing. It depends on the track you're on, though. For the end plates, the Gurney flap is still quite beneficial, with them either increasing the downforce with no drag penalty, or increasing the downforce with decreasing the drag coefficient. So the end plates and the main flap are definitely benefited by this Gurney flap. The flap, which is actually where the Gurney flap is on, is benefited in terms of the downforce, and the drag coefficient may be a benefit, may not be a benefit, depending on that situation. So overall, the Gurney flap is very good for this front wing setup. But there's more to this geometry than just this front structure. There's also the suspension, the tires, and the nose. As shown in Table 1, we can see the effects of the Gurney flap on these different components. So the Gurney flap is actually beneficial for the tire, with it increasing the downforce produced by the tire by 38%, while decreasing the drag of the tire by 26%. That's great. Like, to be able to reduce the drag of a tire is almost impossible from a commercial car point of view, because you can't really do too much with it. For an F1 car, you can do a lot more with it. Reducing the drag by 26% is really nice. Increasing the downforce of the tire is great as well, because again, trying to manipulate the aerodynamics of a tire is very difficult. So however, when it comes to the suspension of the vehicle, the Gurney flap is arguably bad. So for the vehicle body, okay, there is about a 62.9% increase in the downforce, but there's almost a 50% increase in the drag. And again, depending on the track, this might be good, this might be bad. A similar thing can be seen when we have the vehicle body. So we have, again, a significant increase in the downforce, but also a significant increase in the drag as well. So that's the end of this podcast, what we're going through. We found that the Gurney flap, as I kind of suspected, and I'm sure you probably suspected from other podcasts as well, is pretty decent in terms of how well it's increasing the downforce of the car. And okay, we get some increases in the drag as well, but that may be good in some situations. And this not necessarily need to have a Gurney flap which is vertical. It might be at an angle a little bit to effectively approximate like a wing flap, and not just this vertical plate. But overall, it's pretty good. So what about for all of these effects? Let's say the CFD, when we were looking at the setup, I wanted to talk about, with the potential errors that are coming from the CFD setup, are the effects that we are seeing, are they valid or invalid? I would say for this that the results that they found are still valid. And the reason why is that both the trends and the general values are accurate enough, because these values are in the tens of percents. They're not just 3 or 4% changes. So sure, the exact percentage errors that we're finding are probably going to have errors of maybe 2 or 3% based on the CFD setup. But the general trends that we're finding and the general values, so for example, the lift coefficient of the overall car is increased by 24%. That might be 20%, might be 28%, but overall it's around 24%. And that's because the CFD is accurate enough in this situation to give that much leeway in the error. And the trends are definitely accurate. So that's my assessment of this CFD and these results. In the next podcast, we'll look into the flow features and how the Gurney flaps affected them. So we have a bunch of cool little cut planes here with different flow features that we'll look into and how the Gurney flaps affected them. But that's the end of this podcast now. And if you liked it, make sure to like it. If you want to see more like this, click the subscribe button and or follow if you're on Spotify or Google Play. And if you want to get better at CFD like this and or theory that we've been going through, check out our courses that we put on. You can find the link in the description below. And if you want to make your experiments 2 to 4% more accurate, check out Atmosphere Hawk. The reason why it makes your experiments that much more accurate is because the density of air changes by 2 to 4% every day. So when you walk into your wind tunnel in the morning and you come back after lunch, the density of air will be changing throughout that entire time and up to more than 4%. On a regular day, it's about 4%. But if you have like a storm or something, it could be 5, 10, 15%. And when you go between days, weeks, months, and seasons, it changes even more. So 15% is quite common. And if you are not measuring the density of air when you are doing your experiments, you have that error in your experiments. And because in today's day and age, most of the results that we're getting are within a 2 to 4% error. Anyway, like we're only finding like 1 or 2% changes in our results between different setups. The error that we're getting from the density overrides that, so we can't actually find anything. And that's a bigger problem than most people realize. And like when you go through papers like this, like we go through, you find a lot of these errors that people don't even realize, which makes the paper invalid, but they don't realize it. So if you want to make your experiments 2% accurate, check out the Atmosphere Hawk. It's the link we make. It's the instrument we make, and you can find it in the link in the description. And I'll see you next video. Peace out, amigos.